CIET NCERT presents audiobook Ganit Manjari, Part 1, Textbook of Mathematics for Grade 9.
Page number 68. Chapter number 4. Exploring Algebraic Identities. On the page, you are provided with a QR code, scanning which you can reach out to the additional resources to this chapter. 4.1 Introduction. In earlier chapters, you learned about linear polynomials and how they can be used to represent and solve real-life problems. You also studied linear equations and discovered how they describe relationships between quantities. In this chapter, we will take the next step by exploring algebraic identities. These are special mathematical rules that not only make it easier to simplify complicated calculations, but also help us work efficiently with algebraic expressions. Let us begin by exploring a few simple patterns. Example 1. Consider any three consecutive square numbers. For example, 1, 4, and 9. Add the smallest and the largest squares. Thus, 1 plus 9 is equal to 10. Then, subtract twice the middle square from this sum. This leads to 10 minus 2 into 4, that is equal to 10 minus 8 is equal to 2. Now try the same process with another set of three consecutive square numbers, say 9, 16, 25. Here there is a picture of a girl which displays that she is doing the calculations and she checks that 34 minus 2 into 16 is equal to 34 minus 32, that is equal to 2. And she says that the result is always 2. For example, consider the consecutive squares 25, 36, 49. Applying the same rule, we get 25 plus 49 minus 2 into 36 is equal to 74 minus 72, that is equal to 2. Repeat this process with other sets of three consecutive square numbers. The result always seems to be 2 factorial. The pattern may appear surprising, but soon we will uncover the reason behind it using algebra. Page number 69. Think and reflect. Try and find other patterns like this one. For example, you could consider 4 consecutive squares and see if you can find a pattern. 4.2. Visualizing identities. In this section, we will revisit some algebraic identities that we have studied in earlier grades and try to visualize them using geometrical models. In particular, we will use squares and rectangles to represent terms. Consider two line segments of lengths A and B units respectively and make a longer line segment of length A plus B units as displayed in figure 4.1. In figure 4.1, we find a line segment of A units and B units. Combining, it represents A plus B units. We can now construct a square of side A plus B units and partition it into smaller squares and rectangles as displayed in figure 4.2. Here in figure 4.2, we find a square of side length A plus B units. Also, inside this square, we have two smaller squares of side square length of area A square and B square and two rectangles of area AB each. Observe that the area of the outer square is A plus B whole square. Area of the larger square inside the outer square is A square, while the area of the smaller square is B square. Page number 70. The areas of the two rectangles are AB each. Together, they make the bigger square. Hence, we can conclude that A plus B whole square is equal to A square plus 2AB plus B square. From the figure 4.2, it is clear that A plus B whole square is equal to A square plus 2AB plus B square for all A and B, where A and B are lengths of line segments. Think of numbers A and B, where A and B do not represent lengths of line segments. What if A and B are negative numbers? Let us check for some negative numbers and check if this equation still works. Example 2. Let A is equal to -2 and B is equal to -3. Then A plus B is equal to -5 and A plus B whole square is equal to 25. Also, A square is equal to 4, B square is equal to 9 and 2AB is equal to 12. Thus, A square plus 2AB plus B square is equal to 4 plus 12 plus 9 is equal to 25. Hence, A square plus 2AB plus B square is equal to A plus B whole square again. Now suppose A and B are rational numbers. Say A is equal to -2 upon 3 and B is equal to 3 upon 4. Then A plus B is equal to -2 upon 3 plus 3 upon 4. That is equal to 1 upon 12. A plus B whole square is equal to 1 upon 144. A square plus 2AB plus B square is equal to -2 upon 3 whole square plus 2 into -2 upon 3 into 3 upon 4 plus 3 upon 4 whole square. That is equal to 4 upon 9 minus 1 plus 9 upon 16, which is equal to 144 as LCM and 64 minus 144 plus 81 is equal to 145 minus 144 upon 144 is equal to 1 upon 144. So, A square plus 2AB plus B square is equal to A plus B whole square seems to be true for rational numbers too. But we are still not sure if it is true for all numbers. To verify this, let us investigate further using the distributive property of numbers. A plus B whole square is equal to A plus B into A plus B. That is equal to A multiplied by A plus B plus B multiplied by A plus B. That is equal to A square plus AB plus BA plus B square. That is equal to A square plus 2AB plus B square. Recall that in grade 8, you were introduced to A plus B whole square. That is equal to A square plus 2AB plus B square as an identity. What is the difference between an equation and an identity? An algebraic identity is an equation that is true for all values of the variables occurring in it, while an equation need to be true for all values. Page number 71. For example, x square minus 1 is equal to 24 is true for only x is equal to 5 or minus 5. Hence, it is an equation. But x plus y whole square is equal to x square plus 2xy plus y square is true for all values of x and y. Therefore, this equation is also an identity. By now, you must have observed that a plus b whole square is not equal to a square plus b square. But can you find out which one of them will be greater? For example, if a is equal to 10 and b is equal to 2, what are the values of a plus b whole square and a square plus b square? A plus b whole square is equal to 10 plus 2 whole square, that is equal to 12 square, that is equal to 144. And a square plus b square is equal to 10 square plus 2 square, that is equal to 104. So, in this case, a plus b whole square is greater than a square plus b square. But is it true for all numbers a and b? Think and reflect. Question number 1. What can you say about a and b if a plus b whole square is less than a square plus b square? Question number 2. What can you say about a and b if a plus b whole square is greater than a square plus b square? Question number 3. When will a plus b whole square be equal to a square plus b square? Did you observe that a plus b whole square and a square plus b square are both positive? What term will decide which is larger? Use the expansion of a plus b whole square to decide. We can use the identity a plus b whole square is equal to a square plus 2ab plus b square to find the square of general binomial expressions. Example 3. Let us try to expand 5x plus 2y whole square. Here, a is equal to 5x and b is equal to 2y. Then, 5x plus 2y whole square is equal to 5x whole square plus 2 into 5x into 2y plus 2y whole square is equal to 25x square plus 20xy plus 4y square. We can also use the identity to help us with numerical calculations. Example 4. To calculate 43 square, we can write it as 40 plus 3 whole square. That is equal to 40 square plus 2 into 40 into 3 plus 3 square, which is equal to 1600 plus 240 plus 9, which is equal to 1849. Exercise set 4.1. Question number 1. Using the identity a plus b whole square is equal to a square plus 2ab plus b square, expand the following. First part, 7x plus 4y whole square. Second part, 7 upon 5x plus 3 upon 2y whole square. Third part, 2.5p plus 1.5q whole square. Page number 72. Fourth part, 3 upon 4s plus 8t whole square. Fifth part, x plus 1 upon 2y whole square. Sixth part, 1 upon x plus 1 upon y whole square. Question number 2. Using the same identity, find the values of the following. First part, 64 square. Second one, 105 square. Third one, 205 square. 4.3. Factorization of algebraic expressions using identities. The identity a plus b whole square is equal to a square plus 2ab plus b square can also be used to find factors of some algebraic expressions. Example 5. Consider the algebraic expression x square plus 4x plus 4. We observe that x square is equal to x square, 4 is equal to 2 square, and 4x is equal to 2 into 2 into x. Hence, x square plus 4x plus 4 is equal to x square plus 2x into 2 plus 2 square can be compared with a square plus 2 into a into b plus b square, where a is equal to x and b is equal to 2. We conclude that x square plus 4x plus 4 is equal to x plus 2 whole square. Therefore, we can say that x plus 2 is a factor of x square plus 4x plus 4. Example 6. Let us try to find factors of another algebraic expression 36x square plus 12x plus 1. Writing this in the form a square plus 2ab plus b square, we get 36x square plus 12x plus 1 is equal to 6x whole square plus 2 into 6x into 1 plus 1 square, where a is equal to 6x and b is equal to 1. Therefore, 36x square plus 12x plus 1 is equal to 6x plus 1 whole square. Thus, 6x plus 1 is a factor of 36x square plus 12x plus 1. Example 7. Let us try to factor 50p square plus 60pq plus 18q square. What will a and b be in this case? Try to think of a term whose square is 50p square. It is square root of 50 into p. But if we want to avoid using the square root symbol, we may proceed as follows. We observe that 2 is a common factor of the terms 50p square, 60pq and 18q square. Thus, 50p square plus 60pq plus 18q square is equal to 2 within brackets 25p square plus 30pq plus 9q square. Page number 73. Now, let us focus on the expression 25p square plus 30pq plus 9q square. Think of a term whose square is 25p square. What about 9q square? 50p square plus 60pq plus 18q square is equal to 2 within brackets 5p whole square plus 2 into 5p into 3q plus 3q whole square. That is equal to 2 within brackets 5p plus 3q whole square. Here we have used the identity a plus b whole square is equal to a square plus 2ab plus b square to factor the expression 25p square plus 30pq plus 9q square after taking 2 as a common factor. In all the examples described so far, we have used the identity a plus b whole square is equal to a square plus 2ab plus b square to find factors of different algebraic expressions. Think and reflect. What if we replace b by minus b in a plus b whole square is equal to a square plus 2ab plus b square? We get a minus b whole square is equal to a square minus 2ab plus b square, which is also an identity and can be used in ways similar to a plus b whole square is equal to a square plus 2ab plus b square. Let us revisit the pattern we observed in example 1. Any three consecutive numbers can be written as n minus 1, n and n plus 1. Their respective squares are of the form n minus 1 whole square, n square and n plus 1 whole square. The sum of the smallest and the largest squares is n minus 1 whole square plus n plus 1 whole square, that is equal to n square minus 2n plus 1 plus n square plus 2n plus 1, that is equal to 2n square plus 2. Subtracting 2n square from this leads to 2. Hence, you always get 2. This is, in fact, a proof of the fact that if we add the smallest and largest of any three consecutive square numbers and subtract 2 times the middle square number, we will always arrive at 2. Just as the identity a plus b whole square is equal to a square plus 2ab plus b square can be used to find the squares of numbers, we can also use a minus b whole square is equal to a square minus 2ab plus b square in a similar manner. Example 8. Suppose we have to calculate 29 square. We can express this as 30 minus 1 whole square, that is equal to 30 square minus 2 into 30 into 1 plus 1 square, that is equal to 900 minus 60 plus 1, that is equal to 841. To visualize the identity a minus b whole square is equal to a square minus 2ab plus b square, let us draw a square of side a units and split a in two parts, one of length a minus b units and another of length b units. Then the figure would appear like this. Page number 74. Here in figure 4.3, we find a square of side a units in which the side has been split into b and the rest part of the side length a becomes a minus b. Similarly, on the other side of the square, we have side length to be b and a minus b respectively. Thus, we have two rectangles of area AB and b into a minus b and another square of area a minus b whole square. The area of the big square is a square units. The small square has an area of a minus b whole square units. The larger rectangle has area AB square units, while the smaller rectangle has area b into a minus b square units. Thus, to obtain a minus b whole square, we can subtract the areas of the rectangles from the big square. We obtain a minus b whole square is equal to a square minus ab minus b into a minus b, which is equal to a square minus ab minus ba plus b square, that is equal to a square minus 2ab plus b square. Exercise set 4.2. Question number 1. Factor completely. First part, 9x square plus 24xy plus 16y square. Second part, 4s square plus 20st plus 25t square. Page number 75. Third part, 49x square plus 28xy plus 4y square. Fourth part, 64p square plus 32 upon 3 pq plus 4 upon 9 q square. Fifth part, 3a square plus 4ab plus 4 upon 3 b square. Sixth part, 9 upon 5 s square plus 6 sv plus 5v square. Hint provided is 2 was taken out as a common factor in example 7. Is it possible to do something similar in exercises 5 and 6 given here? Question number 2. Find the values of the following using the identity a minus b whole square is equal to a square minus 2ab plus b square. First part 79 square. Second part 193 square. Third part 299 square. 4.4 More identities. What will happen if we want to find the square of the sum of three numbers a, b and c, that is a plus b plus c whole square? Let us replace b plus c by d. We already know a plus d whole square is equal to a square plus 2ad plus d square. Thus, replacing d by b plus c, we get a square plus 2ad plus d square is equal to a square plus 2a into b plus c whole square. So, a plus b plus c whole square is equal to a square plus 2ab plus 2ac plus b square plus 2bc plus c square. It may be more convenient to remember this as a plus b plus c whole square is equal to a square plus b square plus c square plus 2ab plus 2bc plus 2ca. Here we find a picture of a girl wondering that what if I put d is equal to b plus c. Let us interpret this geometrically by drawing a square of side a plus b plus c as displayed in figure 4.4. There is a picture of a boy wondering at the formula a plus b plus c whole square is equal to a plus d whole square. Page number 76. Here in figure 4.4 we have a geometrical model representing the identity a plus b plus c whole square is equal to a square plus b square plus c square plus 2ab plus 2bc plus 2ca, in which we find there is a big square of area a square, another square which is yellow in color and smaller in size is b square, and the smallest square is blue in color. We also have two rectangles of same color orange representing area 2ab and two more rectangles which are purple in color representing area 2bc, and we have two green rectangles representing area 2ca. Think and reflect. Label the squares and rectangles in figure 4.4 so that it represents the identity a plus b plus c whole square is equal to a square plus b square plus c square plus 2ab plus 2bc plus 2ca. Example 9. Let us use this identity to find the square of a number, say 119. 119 square is equal to 100 plus 10 plus 9 whole square. That is equal to 100 square plus 10 square plus 9 square plus 2 into 100 into 10 plus 2 into 100 into 9 plus 2 into 10 into 9. That is equal to 10,000 plus 100 plus 81 plus 2000 plus 1800 plus 180. That is equal to 14,161. So far, we have verified the following three identities and used them for performing calculations and manipulating algebraic expressions. First one, a plus b whole square is equal to a square plus 2ab plus b square. Second one, a minus b whole square is equal to a square minus 2ab plus b square. Third one, a plus b plus c whole square is equal to a square plus b square plus c square plus 2ab plus 2bc plus 2ca. Exercise set 4.3. Question number 1. Find the following squares using one of the given identities. Determine which of these identities will make these calculations easier. First part, 117 square. Second one, 78 square. Third one, 198 square. Fourth, 214 square. Fifth, 1104 square. Sixth, 1120 square. Page number 77. Question number 2. Factor using suitable identities. First part, 16y square minus 24y plus 9. Second part, 9 upon 4 s square plus 6 st plus 4t square. Third part, m square upon 9 plus mk upon 3 plus k square upon 4 plus 3nk plus 2mn plus 9n square. Fourth part, p square upon 16 minus 2 plus 16 upon p square. Fifth part, 9a square plus 4b square plus c square minus 12ab plus 6ac minus 4bc. Question number 3. Expand the following using the identity a plus b plus c whole square is equal to a square plus b square plus c square plus 2ab plus 2bc plus 2ca. First part, p plus 3q plus 7r whole square. Second part, 3x minus 2y plus 4z whole square. Question number 4. Is this an identity? A plus b minus c whole square plus a minus b plus c whole square plus a minus b minus c whole square is equal to 2a square plus 2b square plus 2c square. In grade 8, you were introduced to yet another identity a square minus b square is equal to a plus b into a minus b. This can be quite useful if it is rewritten as a square is equal to within brackets a plus b into within brackets a minus b plus b square. Observe the following figure. Justify the identity a square is equal to a plus b into a minus b plus b square for yourself. Here we have figure 4.5 which represents the identity a plus b into a minus b plus b square is equal to a square. In 750 CE, this identity was proposed by Sridharacharya as a method to quickly compute the squares of numbers. For example, 55 square is equal to 55 plus 5 into 55 minus 5 plus 5 square, that is equal to 60 into 50 plus 25, that is equal to 3000 plus 25, that gives 3025. Page number 78. Think and reflect. Question number 1. Try to evaluate the following using a suitable identity. First part, 35 square. Second part, 65 square. Third part, 85 square. Fourth part, 105 square. Do you observe any interesting pattern? Question number 2. Observe the two rows of figures given here. They represent an algebraic identity. Try to identify it. We have visual display of the identities having the sides a plus b plus c and a plus b minus c, and another square having side a minus b plus c, and there's one more square having side a minus b minus c. We also have another square having side length 2a, another smaller square having side length 2b, and one more square having side length 2c. This is represented in figure 4.6. 4.5 Factorization using algebra tiles. Consider a rectangle with sides x plus 3 and x plus 4 units. We know that the area of such a rectangle is x plus 3 into x plus 4 square units. Using distributivity, we get x plus 3 into x plus 4 is equal to x square plus 3x plus 4x plus 12. That is equal to x square plus 7x plus 12. Page number 79. Here we are provided with figure 4.7, which explains factorization of x square plus 7x plus 12. We find in the figure a square of side lengths x plus 3 and another side of this rectangle is measuring x plus 4, which is made up of a square having area x square, and there are 3 rectangles of area x into 1, and there are 4 more rectangles of area x into 1, and we can find here 12 squares of unit area 1. Figure 4.7 helps to visualize the product of x plus 3 and x plus 4 using algebra tiles. The expression x plus 3 is represented using an x tile and 3 unit tiles. Similarly, x plus 4 is represented using an x tile and 4 unit tiles. The product of these two linear factors is displayed in the inner rectangle, comprising the x square tile, the 7 x tiles and 12 unit tiles. Note that the 7x in x square plus 7x plus 12 has been split as 3x plus 4x. This is represented by the fact that 3 x tiles are placed on the right side of the x square tile and 4 x tiles are arranged below it. Also, the 12 unit tiles are arranged in a 3 by 4 array. Once the rectangular arrangement is formed, we observe that the dimensions of the rectangle are x plus 3 and x plus 4 units respectively. Think and reflect. Suppose 7x is split as 2x plus 5x. Can a similar rectangular arrangement be formed? Consider other possibilities and check. Figure 4.7 helps us to visualize two algebraic identities. First one, the linear expressions x plus 3 and x plus 4 can be multiplied to obtain the identity x plus 3 into x plus 4, that is equal to x square plus 7x plus 12. Second one, also the expression x square plus 7x plus 12 can be factored into the linear factors x plus 3 and x plus 4, giving the same identity x square plus 7x plus 12 is equal to x plus 3 into x plus 4. Think and reflect. Algebra tiles can be used to represent products and find factors. First one, figure out the product of x plus 2 and x plus 3 using algebra tiles. Second one, lay out algebra tiles for x square plus 11x plus 30 in such a way that you will observe its factors. Page number 80. Think and reflect. We have noticed that x plus 3 into x plus 4 is equal to x square plus 7x plus 12. Also, x plus 6 multiplied by x plus 7 is equal to x square plus 13x plus 42. Generalize the pattern to get an expression for x plus a into x plus b. Now consider the case where we have a rectangle of side lengths 2x plus 3 and 3x plus 1 as given in figure 4.8. What can you say about its area 2x plus 3 into 3x plus 1? Here in figure 4.8, using algebra tiles to represent 2x plus 3 into 3x plus 1 is given here. We have x square tiles which are 6 in number, and there are unit tiles which are 3, and we have rectangular tiles which are 11 in number. They have been arranged in rectangular format with side lengths 3x plus 1 and 2x plus 3. Fill in the blanks with the appropriate expressions to make the equation true. Px plus a multiplied by qx plus b is equal to dash x square plus dash into x plus dash. Also, verify your answer using the distributive property. 4.6 Factorization without using algebra tiles. Consider the algebraic expression x square plus 7x plus 12, which was obtained by multiplying the linear terms x plus 3 and x plus 4. We also noticed in figure 4.7 that 7x was split as 3x plus 4x, so that a rectangle could be formed using the algebra tiles. But how do we achieve this splitting of x term without using tiles? Page number 81. Example 10. Let us begin with x square plus 7x plus 12 is equal to x square plus a plus b into x plus ab. Comparing the coefficients of the x term and the constant terms on both sides of the equation, we get a plus b is equal to 7 and a into b is equal to 12. Note that this is only possible when a is equal to 3 and b is equal to 4, or a is equal to 4 and b is equal to 3. Thus, we choose one of these two possibilities and write the factors as x plus a into x plus b, that is x plus 3 into x plus 4. Example 11. Let us try to factor x square plus 11x plus 30 in a similar manner. X square plus 11x plus 30 is equal to x square plus a plus b into x plus ab. This leads to a plus b is equal to 11 and a into b is equal to 30. We need to choose values of a and b appropriately so that a plus b is equal to 11 and ab is equal to 30 are both satisfied. What if we choose a is equal to 2 and b is equal to 15, or a is equal to 3 and b is equal to 10? Clearly, these will not work as a plus b is not equal to 11, even though a into b is equal to 30. So, we look at the factors of 30 and arrive at a is equal to 5 and b is equal to 6, or vice versa. This way, the x term 11x can be split as 5x plus 6x. Thus, x square plus 11x plus 30 is equal to x square plus 5 plus 6 within brackets into x plus 30, that is equal to x plus 5 into x plus 6. Example 12. In order to factor x square minus 5x plus 6, we first note that the coefficient of x is negative. Once again, comparing x square minus 5x plus 6 with x square plus a plus b into x plus ab, we get a plus b is equal to minus 5 and a into b is equal to 6. Note that these two equations can be satisfied together only when a is equal to minus 2 and b is equal to minus 3, or vice versa. Exercise set 4.4. Question number 1. Fill in the blanks to complete the following identities. First part, s square minus 11s plus 24 is equal to dash into dash. Second, dash multiplied by x plus 1 is equal to 3x square minus 4x minus 7. Third part, 10x square minus 11x minus 6 is equal to 2x minus dash as one factor multiplied by dash plus 2 as another factor. Fourth part, 6x square plus 7x plus 2 is equal to dash multiplied by dash. Question number 2. Select and use the identity that will help you to find the following products without multiplying directly. First part, 41 square. Second part, 27 square. Third part, 23 into 17. Fourth part, 135 square. Page number 82. Fifth part, 97 square. Sixth part, 18 into 29. Seventh part, 34 into 43. Eighth part, 205 square. Question number 3. Factor the following. First part, 9a square plus b square plus 4c square minus 6ab plus 12ac minus 4bc. Second part, 16s square plus 25t square minus 40st. Third part, r square minus r minus 42. Fourth part, 49g square plus 14gh plus h square. Fifth part, 64u square plus 121v square plus 4w square minus 176uv minus 32uw plus 44vw. Think and reflect. James and Reshma were talking about algebraic identities they learnt in school. James says a minus b whole square into a plus b is equal to a square minus 2ab plus b square multiplied by a plus b. Reshma says, I have a different idea. A minus b whole square multiplied by a plus b is equal to a minus b. Taking common, we have a minus b into a plus b, that is equal to a minus b into a square minus b square. I will find this product to get the answer. According to you, who is correct and why? Try to combine more such identities and find new results. 4.7. Finding new identities. In this section, we will play around with algebraic expressions to observe if we can arrive at new identities. What do you think a plus b whole cube will look like? Let us find out the answer using the distributive property. A plus b whole cube is equal to a plus b into a square plus 2ab plus b square. That is equal to a cube plus 3a square b plus 3ab square plus b cube. Here we have found a new identity, namely a plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. Let us try to visualize this identity. We notice that a square of side a plus b can be divided into squares and rectangles. This led us to the identity a plus b whole square is equal to a square plus 2ab plus b square. What if we have a cube of edge a plus b? Can we divide a cube of edge a plus b into smaller cubes and cuboids and represent this new identity? Here we have a figure 4.9 of a cube of edge a plus b. We find there is a cube having the side length a plus b. Page number 83. We know that the volume of this cube is a plus b whole cube. Let us split this cube into smaller cubes and cuboids. Here in figure 4.10, representation of the identity a plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube has been given. In three different pictures, the cubes have been split into smaller cubes and cuboids. To express the identity a plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. Notice that the larger cube can be split into 2 cubes and 6 cuboids. The cubes have volumes a cube and b cube cubic units respectively. Amongst the other 6 cuboids, 3 have dimensions a units into a units into b units, and other 3 have dimensions a units into b units into b units, and so their volumes are a square b and ab square cubic units respectively. Hence, the total volume of the 6 cuboids is 3a square b plus 3ab square. Page number 84. This gives us a plus b whole cube is equal to a plus b into a square plus 2ab plus b square, that is equal to a cube plus 3a square b plus 3ab square plus b cube. Here we have found a new identity, namely a plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. What happens when we replace b with minus b in this new identity? A plus minus b within brackets whole cube can be written as a cube plus 3a square multiplied by minus b plus 3a multiplied by minus b whole square plus minus b whole cube. This leads to the identity a minus b whole cube is equal to a cube minus 3a square b plus 3ab square minus b cube. Note that out of the 4 terms, 2 are positive and 2 are negative. They appear alternately in the expression. Let us observe how we can use these new identities. Example 13. What is the side of the cube whose volume is p cube plus 6p square q plus 12p q square plus 8q cube cubic units? Comparing p cube plus 6p square q plus 12 pq square plus 8q cube with the right side of the identity a plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. We may rewrite it as p cube plus 3 into p square into 2q plus 3 into p into 2q whole square plus 2q whole cube, which is p plus 2q whole cube, so that a is equal to p and b is equal to 2q. Hence, a side of the cube will be p plus 2q units. Example 14. Now consider the expression 8n cube minus 60n square m plus 150 nm square minus 125 m cube. If you write it in the form a minus b whole cube, what will be a and b? Rewriting the expression 8n cube minus 60n square m plus 150 nm square minus 125 m cube as 2n whole cube minus 3 into 2n whole square into 5m plus 3 into 2n into 5m whole square minus 5m whole cube, and comparing it with a cube minus 3a square b plus 3ab square minus b cube is equal to a minus b whole cube. We get 2n minus 5m whole cube. Hence, a is equal to 2n and b is equal to 5n. Now, let us play with known identities to discover more identities. Try to multiply the following using the distributive property. First one, x minus y multiplied by x square plus xy plus y square. Second one, x plus y multiplied by x square minus xy plus y square. Let us work out the product of the first one. X minus y multiplied by x square plus xy plus y square is equal to x cube plus x square y plus xy square minus x square y minus xy square minus y cube. That is equal to x cube plus x square y plus xy square minus x square y minus xy square minus y cube is equal to x cube minus y cube. Page number 85. Thus, x minus y into x square plus xy plus y square is equal to x cube minus y cube. This is also an identity. Verify this for yourself by choosing different values of x and y. Predict what x plus y into x square minus xy plus y square will be. Think and reflect. We already know that x square minus y square is equal to x minus y into x plus y. Further, we have verified that x cube minus y cube is equal to x minus y into x square plus xy plus y square. Observe that x minus y is a common factor of x square minus y square and x cube minus y cube. Do you think x minus y is also a factor of x to the power 4 minus y to the power 4? Note that x to the power 4 minus y to the power 4 is equal to x square the whole square minus y square whole square is equal to x square minus y square multiplied by x square plus y square. Can you notice how x minus y is a factor of x to the power 4 minus y to the power 4? How about x to the power 5 minus y to the power 5? Does this also have x minus y as a factor? Exploring further, let us multiply x plus y plus z and x square plus y square plus z square minus xy minus xz minus yz. X plus y plus z multiplied by x square plus y square plus z square minus xy minus xz minus yz is equal to x cube plus xy square plus xz square minus x square y minus x square z minus xyz plus x square y plus y cube plus yz square minus xy square minus xyz minus y square z plus x square z plus y square z plus z cube minus xyz minus xz square minus yz square, that is equal to x cube plus xy square plus xz square minus x square y minus x square z minus xyz plus x square y plus y cube plus yz square minus xy square minus xyz minus y square z plus x square z plus y square z plus z cube minus xyz minus xz square minus yz square. After cancelling out the common terms, we have x cube plus y cube plus z cube minus 3xyz. So, x plus y plus z into x square plus y square plus z square minus xy minus xz minus yz is equal to x cube plus y cube plus z cube minus 3xyz. This is yet another identity. Let us explore some of its applications. Example 15. The sum of three numbers is 10 and their product is 25. The sum of their squares is 38. Try to use the previous identity to find the sum of the cubes of these three numbers. Let the three numbers be x, y and z, respectively. According to the problem, x plus y plus z is equal to 10, x into y into z is equal to 25 and x square plus y square plus z square is equal to 38. Substituting in the identity, x plus y plus z multiplied by x square plus y square plus z square minus xy minus xz minus yz is equal to x cube plus y cube plus z cube minus 3xyz. We get 10 multiplied by 38 minus xy minus xz minus yz, that is equal to x cube plus y cube plus z cube minus 3 into 25. Thus, x cube plus y cube plus z cube is equal to 380 minus 10 into within brackets xy plus xz plus yz plus 75 is equal to 455 minus 10 multiplied by xy plus xz plus yz. Page number 86. To find x plus y plus z whole square is equal to x square plus y square plus z square plus 2xy plus 2xz plus 2yz. We get 100 is equal to 38 plus 2 into xy plus xz plus yz. Thus, xy plus xz plus yz is equal to 31. Now substituting this into our earlier equation, we obtain x cube plus y cube plus z cube is equal to 455 minus 10 into xy plus xz plus yz, that is equal to 455 minus 10 into 31, that is equal to 455 minus 310 is equal to 145. 4.8. Simplifying rational expressions. In the earlier sections of this chapter, we have learned how to factorize algebraic expressions. Let us observe how we can simplify some rational algebraic expressions using factorization. Example 16. Simplify the rational expression x square minus 7x plus 12 upon 5x square plus 5x minus 100, assuming that 5x square plus 5x minus 100 is not equal to 0. In order to simplify this rational expression, we need to cancel the common factors between the expressions in the numerator and denominator. We will need to use algebraic identities to simplify this rational expression. First, let us observe the numerator x square minus 7x plus 12. We need to find a and b such that a plus b is equal to minus 7 and ab is equal to 12. Can you think of two such numbers? They are minus 3 and minus 4. Factor the expression, we get x square minus 7x plus 12 is equal to x minus 3 into x minus 4. Now, let us observe the denominator. 5x square plus 5x minus 100. We can notice that all the three terms are multiples of 5. So, we can take 5 as a common factor and simplify the expression. 5x square plus 5x minus 100 is equal to 5 within brackets x square plus x minus 20. Now, we need to find a and b such that a plus b is equal to 1 and ab is equal to minus 20. Try to think of two such numbers. They are 5 and minus 4. Thus, we have 5x square plus 5x minus 100 is equal to 5 into x minus 4 into x plus 5. Substituting the factored expressions in the numerator and denominator, we arrive at x square minus 7x plus 12 upon 5x square plus 5x minus 100 is equal to x square minus 7x plus 12 upon 5 into x square plus x minus 20 in brackets is equal to x minus 4 into x minus 3 in numerator and 5 into x minus 4 into x plus 5 in denominator. Thus, the common factor x minus 4 can be cancelled as it is not equal to 0. We know this because 5x square plus 5x minus 100 is not equal to 0. Thus, x square minus 7x plus 12 upon 5x square plus 5x minus 100 is equal to x minus 3 upon 5 into x plus 5. Page number 87. Think and reflect. Try to simplify the following rational expression. 36 s square minus 12 st plus t square upon t square plus 2ts minus 48 s square is equal to 6s minus t whole square upon dash plus dash as one factor, dash plus dash as another factor. Hint: factor t square plus 2ts minus 48s square and simplify the rational expressions assuming that t square plus 2ts minus 48s square is not equal to 0. Exercise set 4.5. Question number 1. Simplify the following rational expressions assuming that the expressions in the denominators are not equal to 0. First part, 3p square minus 3pq minus 18q square upon p square plus 3pq minus 10q square. Second part, n cube minus 3n square m plus 3nm square minus m cube upon 5m square minus 10mn plus 5n square. Third part, w cube minus v cube plus x cube plus 3wvx divided by w square plus v square plus x square minus 2wv minus 2vx plus 2wx. Fourth part, 4y square minus 20yz plus 25z square divided by 25z square minus 4y square. Fifth part, x square plus x minus 6 multiplied by x square minus 7x plus 12 divided by x square minus 6x plus 8 into x square minus 9. Sixth part, p to the power 4 minus 16 divided by p square minus 4p plus 4. Example 17. Saira has arranged a square of side x units, 8 rectangular strips of sides x units and width 1 unit, and 15 squares of side 1 unit to form a bigger rectangle. Find the length and breadth of the rectangle in terms of x. Area covered by a square of side x units is equal to x square square units. Area covered by rectangle of sides x units and 1 unit is equal to x square units. Total area covered by 8 such rectangles is equal to 8x square units. Area covered by a square of side 1 unit is equal to 1 square units. Total area covered by 15 such squares is equal to 15 square units. Total area covered by all the squares and rectangles is equal to x square plus 8x plus 15 square units. Area of Saira's rectangle is equal to x square plus 8x plus 15 square units. We can factor x square plus 8x plus 15 to obtain the dimensions of the rectangle prepared by Saira. Page number 88. For factoring x square plus 8x plus 15, we need a and b such that a plus b is equal to 8 and a into b is equal to 15. So, a is equal to 3 and b is equal to 5 is one possibility. The possible length and breadth of Saira's rectangle in terms of x are: length is equal to x plus 5 units and breadth is equal to x plus 3 units. Now, draw Saira's rectangle using these pieces. Example 18. A rectangular pool is such that its breadth is 4 meters less than its length and its area is 96 square meters. Find the length and breadth of the pool. Let the length of the pool be x meters, then the breadth of the pool is x minus 4 meters. Since the area is given to be 96 square meters, we get x into x minus 4 is equal to 96. X square minus 4x is equal to 96, or x square minus 4x minus 96 is equal to 0. We choose appropriate factors of minus 96 to split the term minus 4x. We know that minus 12 into 8 is equal to minus 96 and minus 12 plus 8 is equal to minus 4. Hence, minus 4x can be written as minus 12x plus 8x. X square minus 4x minus 96 is equal to x square minus 12x plus 8x minus 96 is equal to x into x minus 12 plus 8 into x minus 12. That is equal to x minus 12 into x plus 8 is equal to 0. Thus, x square minus 4x minus 96 is equal to 0 implies that x minus 12 into x plus 8 is equal to 0. This means either x minus 12 is equal to 0 or x plus 8 is equal to 0. That is, x is equal to 12 or x is equal to minus 8. Since x is the length of the pool, it cannot be negative. Therefore, we ignore x is equal to minus 8 and x is equal to 12 meters must be the length of the pool. The breadth of the pool is equal to x minus 4, that is equal to 12 minus 4 equal to 8 meters. End of chapter exercises. Question number 1. Use suitable identities to find the following products. First part, minus 3x plus 4 whole square. Second part, 2s plus 7 into 2s minus 7. Third part, p square plus 1 upon 2 into p square minus 1 upon 2. Fourth part, 2n plus 7 into 2n minus 7. Fifth part, s minus 2t into s square plus 2st plus 4t square. Sixth part, 1 upon 2r minus 4r whole square. Seventh part, minus 3m plus 4k minus l whole square. Eighth part, x minus 1 upon 3 y whole cube. Ninth part, 7 upon 2k minus 2 upon 3 m whole cube. Page number 89. Question number 2. Find the values using suitable identities. First part, 17 into 21. Second part, 104 into 96. Third part, 24 into 16. Fourth part, 147 whole cube. Fifth part, 199 whole cube. Sixth part, 127 whole cube. Seventh part, minus 107 whole cube. Eighth part, minus 299 whole cube. Question number 3. Factor the following algebraic expressions. First part, 4y square plus 1 plus 1 upon 16y square. Second part, 9m square minus 1 upon 25n square. Third part, 27b cube minus 1 upon 64b cube. Fourth part, x square plus 5x upon 6 plus 1 upon 6. Fifth part, 27u cube minus 1 upon 125 minus 27u square upon 5 plus 9u upon 25. Sixth part, 64y cube plus 1 upon 125 z cube. Seventh part, p cube plus 27q cube plus r cube minus 9pqr. Eighth part, 9m square minus 12m plus 4. Ninth part, 9x cube minus 8 upon 3 y cube plus z cube upon 3 plus 6xyz. Tenth part, 4x square plus 9y square plus 36z square plus 12xz plus 36yz plus 24xy. 11th part, 27u cube minus 1 upon 216 minus 9u square upon 2 plus u upon 4. Question number 4. Simplify the following. First part, 4x square plus 4x plus 1 upon 4x square minus 1. Second part, 9 into 3a cube minus 24b cube upon 9a square minus 36b square. Third part, s cube plus 125t cube upon s square minus 2st minus 35t square. Note, assume that the denominators are not equal to 0. Question number 5. Find possible expressions for the length and breadth of each of the following rectangles whose areas are given by the following expressions in square units. First part, 25a square minus 30ab plus 9b square. Second part, 36s square minus 49t square. Question number 6. Find possible expressions for the length, breadth and heights of each of the following cuboids whose volumes are given by the following expressions in cubic units. First part, 6a square minus 24b square. Second part, 3p square minus 15ps plus 12p. Page number 90. Question number 7. The village playground is shaped as a square of side 40 meters. A path of width s meters is created around the playground for people to walk. Find an expression for the area of the path in terms of s. Question number 8. If a number plus its reciprocal equals 10 upon 3, find the number. Question number 9. A rectangular pool has area 2x square plus 7x plus 3 square hastas. If the width is 2x plus 1 hastas, find its length. Hasta was a unit used to measure length. Question number 10. If both x minus 2 and x minus 1 upon 2 are factors of px square plus 5x plus r, show that p is equal to r. Question number 11. If a plus b plus c is equal to 5 and ab plus bc plus ca is equal to 10, then prove that a cube plus b cube plus c cube minus 3abc is equal to minus 25. Question number 12. By factoring the expression, check that n cube minus n is always divisible by 6 for all natural numbers n. Give reasons. Question number 13. Find the value of first part, x cube plus y cube minus 12xy plus 64 when x plus y is equal to minus 4. Second part, x cube minus 8y cube minus 36xy minus 216 when x is equal to 2y plus 6. Chapter summary. Identities are equations that are true for all values of the variables. One of the ways to visualize identities is using geometrical models or algebra tiles. Identities can also be used to factor algebraic expressions. Factorization of quadratic expressions may be visualized by means of algebra tiles. Identities can also be used to simplify calculations such as squaring numbers or evaluating products of numbers. Rational algebraic expressions may be simplified by factorization and removing the common factors in the numerator and denominator provided such a factor exists and it is not equal to 0. Page number 91. We have studied the following identities in this chapter. X plus y whole square is equal to x square plus 2xy plus y square. X minus y whole square is equal to x square minus 2xy plus y square. X plus y plus z whole square is equal to x square plus y square plus z square plus 2xy plus 2yz plus 2zx. X plus y into x minus y is equal to x square minus y square. X plus a into x plus b is equal to x square plus a plus b into x plus ab. Ax plus b into cx plus d is equal to acx square plus ad plus bc into x plus bd. X cube minus y cube is equal to x minus y into x square plus xy plus y square. X cube plus y cube is equal to x plus y into x square minus xy plus y square. X plus y whole cube is equal to x cube plus 3x square y plus 3xy square plus y cube. X minus y whole cube is equal to x cube minus 3x square y plus 3xy square minus y cube. X cube plus y cube plus z cube minus 3xyz is equal to x plus y plus z into x square plus y square plus z square minus xy minus xz minus yz. Chapter 4 ends here.
Ganit Manjari, Part 1. You were just listening to this audiobook. Textbook of Mathematics for Grade 9. Narration Swarnlata Sharma. Sound recordist Mohammad Faizan Khan. Assistance in production Surendra Kumar. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.